Okay, welcome everyone. It looks like today is a bit more crowded than usual, and I apologize for the fact that we don't have enough sandwiches for everyone. That's a big crowd that we have today. We just had an excellent colloquium by Sylvia Biscoveanu. Did I say it right? Yeah. Okay. Sylvia gave us an update on all the important data from the LIGO Virgo-Kagra collaboration, a very exciting frontier in cosmology and astrophysics, and we'll hear more from her in a few minutes. I also wanted to mention that we will have at the end of this lunch, we will take a photo, as we usually do at the beginning of the academic year. So everyone is invited to step out at the end of the 4 presentations, and it would just be a few minutes. We take a photo and then we can go on to pursue science. So after Sylvia, we'll hear from Sanskriti Das from Stanford, over there, who will tell us about hot circumgalactic medium, the treasure trove of galaxies. And then after that, from Jiaxuan, that I probably didn't say right. How do you say it?
Jiaxuan.
Okay. Lee from Princeton as well. So we have 2 Princeton colleagues today. Who will tell us about dwarfs, near and far. By dwarfs you mean stars or galaxies?
Dwarf galaxies and dwarf planets.
Oh, dwarf planets.
That's the near part.
So you're into dwarfs of both types. Okay. And then we'll hear from Trivedi, who is visiting us from Vanderbilt, and he will talk about a new window to dark matter that involves Planck relics. We'll start with Sylvia.
Okay. Hi, my name is Sylvia Biscoveanu. For those who didn't hear my talk an hour ago, I'm a new faculty member in the physics department at Princeton. So an hour ago, I shared about everything that we have detected with the LIGO Virgo-Kagra ground-based gravitational wave detectors. For the next 10 minutes, I'm going to tell you about a kind of signal that we haven't yet detected, but which we hopefully will soon. And this is the stochastic gravitational wave background. So this is a random gravitational wave signal that's produced by many overlapping but individually indistinguishable sources. You may have heard about the detection of the stochastic gravitational wave background in the nanohertz band for gravitational waves by pulsar timing array experiments. I'm going to be talking about the stochastic background in the LIGO band. So instead of in the nanohertz regime, we're talking in the tens to thousands of hertz range. So this background can be both astrophysical and cosmological in origin. The astrophysical background, as we'll see for the rest of the talk, is going to come from basically all of the very far away, very weak binary black hole and binary neutron star mergers that we don't individually resolve with our detectors. And the cosmological background is basically just the gravitational analog of the CMB. It should be coming from primordial universe processes. So in contrast to the gravitational waves from compact binary mergers, which we are detecting, this kind of signal is persistent and unmodeled. So it's persistent because it's always on, and it's unmodeled because we basically assume that it's a Gaussian random process, although in a few slides I'll tell you about why that's a bad assumption and how we can relax it. So in contrast to the gravitational waves that we do regularly detect a couple times a week now with the LIGO detectors, those are transient. They're short bursts of gravitational radiation that we detect just the final moments of the signal just before merger. And we have a very good model for what that gravitational wave signal should look like depending on the parameters of the binary and that we get from general relativity. So when we talk about characterizing the stochastic gravitational wave background, we use this quantity called omega GW. So this is analogous to omega matter or omega baryon. It is just the sliver of the pie of total energy density in the universe that comes from gravitational waves. And like good astronomers, we assume that the spectrum of this gravitational wave background as a function of frequency follows a power law. And so we are trying to characterize the slope of that power law and the amplitude. So The astrophysical and cosmological stochastic gravitational wave backgrounds are expected to have different properties. So this background of astrophysical origin from all the unresolved compact binary coalescences is expected to be highly non-Gaussian with an estimated amplitude of about omega GW of 10 to the minus 9. And it's highly non-Gaussian because the time between mergers is much longer than the duration of the mergers themselves in the LIGO band. So for example, a 30 solar mass, equal mass binary black hole merger, we see less than a second of this signal, but binary black holes only merge about every 200 seconds in the universe. So we're going a long time between mergers, and so they don't actually overlap to form a truly Gaussian background. They're producing a Poisson background or a popcorn background, and we call it a popcorn background because it sounds like popcorn going off in the microwave. In contrast, the primordial backgrounds from cosmological sources are expected to be Gaussian, but they are much, much weaker. And so here you can see the omega GW spectrum as a function of frequency for different backgrounds and the sensitivity of different experiments. So the binary black hole and binary neutron star backgrounds, again, peak around 10 to the minus 9 in this tens to thousands of hertz range. And you can see that with our LIGO detectors, this plot is now many years out of date, but it's still a nice illustration. With our LIGO detectors, we should be able to be sensitive enough to detect this astrophysical background. Then at the time of this plot, in the nanohertz regime, we only had an upper limit from pulsars. This is now a detection, and this stochastic background comes from the slow in spiral of supermassive black hole binaries, so a totally different kind of astrophysical source. But consistent across basically all frequencies is the background from primordial sources. So for example, from slow roll inflation, you can see that this background is expected to have an amplitude of about 10 to the minus 15. And we can also compare this to the limits that we are putting from the absence of the detection of B-mode polarizations in the CMB, although that's often expressed in terms of a scalar to tensor ratio. This is, you can directly convert that into an omega GW. And so basically, in order to distinguish this kind of primordial signal from the astrophysical signal, we want to exploit these different properties. And so when we look for this signal using typical techniques, we make this assumption that the background is isotropic, unpolarized, stationary, and Gaussian, although this is suboptimal, as I've mentioned. And basically, we assume that the background is going to be more or less the same in two widely separated detectors. And so you can multiply or cross-correlate the data streams from your two detectors. This will basically cancel out any sources of noise that we expect to be unique to each detector. And any kind of excess power that we find, we attribute to an astrophysical signal. And this is the cross-correlated search analysis. And we have done this with the latest LIGO Virgo Kagra data. So these are the latest upper limits using data from the first half of our ongoing fourth observing run. And you can see here our constraints on the amplitude and the slope of this background. So at a slope of alpha equals 2/3, which is what we expect for an astrophysical background, we have a constraint on omega GW to be less than 2 times 10 to the minus 9. And then we can also look at a slope of 0, which is what we expect for a primordial background. And it's slightly higher, 2.8 times 10 to the minus 9. There's this weird peak here, and this is just basically due to noise. But then we can also turn our upper limits and combine them with the information that we have about the population of binary black hole mergers from our individual detections to look at what we expect the spectrum of omega GW to look like based on that population. So this is our current sensitivity to the background in blue. You can see that we're still a little ways off from the predicted background. But the fact that we haven't detected a background allows us to also constrain the evolution of the merger rate of binary black holes as a function of redshift, because if there were loads of binary black hole mergers at redshift of about 3 to 4, then they would have produced a background that we would have been able to see. And so by nature of the fact that we haven't, we can rule out a high merger rate density at large redshifts. So in contrast to the cross-correlation search, we can relax this assumption of Gaussianity and build a more statistically optimal search. So instead, in this Bayesian search method, we model the background as the superposition of an unknown number of mergers, and we can basically leverage the fact that we know exactly what the gravitational wave signal should look like for a binary black hole merger rather than assuming that it's a random Gaussian background. And so when we do this, we actually constrain this astrophysical duty cycle parameter, which is just the fraction of data segments that we analyze that contain a merger. And we don't know in any given segment really if there is a merger or there isn't, but when we analyze a large ensemble of data segments, then we can get a population level constraint on this astrophysical duty cycle. And so when you build in these extra statistical assumptions into your search method, we find that this actually reduces the time to detection for the binary black hole background from months of data at the upgraded sensitivity of LIGO to a few days of data at the current sensitivity. It turns out that actually implementing this search, because it's so sensitive and really relies on these detailed statistical assumptions, when you try to apply this to real data, you have to deal with real data problems like the fact that our detector data, the noise is actually not Gaussian, and we have non-Gaussianities called glitches, and so it's a little bit more complicated, and so we're working on it, but stay tuned because hopefully we should have results from this accelerated search in the coming year or so. And so recently with an undergraduate student at Northwestern, we wanted to see if we do eventually run this Bayesian search, what can we actually learn from this kind of search method about the population of high redshift binary black holes. And so we find that most of the information in this kind of Bayesian search is coming from events with signal to noise ratio around 5 to 7, so basically just below the threshold where we would claim that an individual event has been detected with high confidence. And if we use our Bayesian search in order to constrain the redshift distribution of binary black hole mergers, we are actually able to get information about the shape of the redshift distribution of binary black holes at redshifts beyond the peak of star formation. And so in blue, you can see our constraints for a simulated population that we might be able to get if we run this search. And they're much better than our constraints in red, which is what we would get if we only looked at the events that we can detect individually. And so with that, I'll just flash up my conclusions and urge you to stay tuned, and hopefully in the next few years, we'll be able to have some interesting and exciting constraints on the stochastic gravitational wave background from binary black holes in the LIGO band. Thanks.
This is very exciting, Sylvia. There was one cosmic background that we neglected to mention. Your plot went all the way to gigahertz, and just like the cosmic microwave background, we may have, if inflation didn't take place, there may be a gravitational wave cosmic background at gigahertz, just the same frequency almost as a microwave background. Of course, the temperature is about 1 degree Kelvin instead of 3 degrees Kelvin. That would have been erased by inflation. So detecting it would falsify inflation. That's one way to show that inflation is.
Yes, there are a whole host of more exotic cosmological backgrounds that I did not mention.
Oh, no, I wouldn't call it exotic because we don't know that inflation took place.
Okay.
Anyway, okay. We have 2 hands. Go ahead.
Okay, sort of side question. So you mentioned that there's gravitational wave merger, black hole merger every 200 seconds.
Yes.
This assumes that there must be supernova happening every 100 seconds. Why aren't we seeing them?
They're too far away. Yeah.
Okay.
Go ahead.
This is really interesting. I didn't know this was a thing. So, what is this quantity y that you're actually measuring? Is this like a time average visibility of complex strain between the two detectors?
Yeah, it's basically a cross power spectrum. And then, so when we characterize the noise in a single detector, we calculate an analogous quantity, except instead of multiplying the strain data in one detector with the strain data from another detector, we just multiply the strain data from a given detector with itself. And this is an auto power spectrum. And then you just apply a whole bunch of normalization constants, critical energy needed to close the universe, and H naught, and factors of 2, and then you get something that has the right units for a Trivedi.
And of course, there is also the white dwarfs in the Milky Way that produce another peak syndrome.
Yes, so the white dwarfs in the Milky Way are going to peak in the millihertz regime in the LISA band for the space-based gravitational wave detector LISA, so we won't see those with LIGO. Yeah.
Any other questions, comments? Yes, go ahead. Is someone there?
Might be a dumb question, but the Earth's normal mode, like what is that? Is that the noise that you're talking about per instrument, or just like?
No, this is a weird, so you basically use the Earth as a giant resonant gravitational wave detector, and so if a gravitational wave were to pass by us at a frequency of around, a millihertz, then it would cause the Earth to resonate, and so you can basically use a giant array of seismometers to measure these normal modes of the Earth and see if they are resonating due to a passing gravitational wave, and you can turn that into a constraint on omega GW. Yeah. All right.
Thank you
Thank
so
you.
much, Sylvia.
Ten to the minus 15 hertz is the evolution of new luminoids.
Yeah, you can start.
Hello everyone, I'm Sanskriti. I'm a Hubble Fellow at Stanford University. So I'm generally, so compared to the previous talk on compact objects, now I'm going to switch on very diffuse objects in this talk. I'm interested generally in diffuse gas across different phases and different spatial scales, and today I'm going to focus on the hot circumgalactic medium, which is one of the least observed component of galaxies. So what is circumgalactic medium? It's anything that's beyond the interstellar medium and extended out to the virial radius. So if you take a Milky Way-like galaxy, then the 30 kiloparsec radius is the extent of the interstellar medium, and there is 1,000 times larger volume of gas and metals that is filling up this region. And by construction, it connects the ISM to the IGN. So it controls all the inflows and outflows and accretion, and naturally controls the galaxy evolution. And just because of the very low surface brightness, it's been very challenging to observe. But just because it is also multi-phase, in principle, we can observe it across the electromagnetic spectrum, from radio, where we can observe the neutral CGM, to X-ray, where we can observe the fully ionized or gas. Now, broadly speaking, we can split the observations into two components. One is the observation of metals, where from optical UV to X-ray, where we can see different metals across different ionization states. And in radio, we can see 21 centimeter emissions, which is coming from neutral hydrogen. And also, if we want to trace the total ionized variance instead of just ionized metals, we can use FRDs and SZ effect in millimeter, and that's what I'm going to talk about today. Now, broadly speaking, we already understand galaxies kind of well, then why do we even care about the CGM? There are kind of very basic three unsolved problems that we can try to address by observing CGM across phases. One of them is the missing galactic variance problem. It is often confused with missing variance problem. It is slightly different because on an average scale, we know there must be a lot of gas in the cosmic wave. But the question is, we expect the baryon to dark matter ratio to be something from cosmology, which is constrained well, even in massive halos like galaxy clusters. But as we come down to a level of galaxies, we often see that the interstellar medium and stars account for at most only 20% of the baryons. So the question is, where is that 80% of baryons, and is all galaxies losing that baryons? So how does the baryon fraction of galaxies vary across galactic properties? Is it just mass, or there are different properties controlling the baryon fraction? And if they are retaining all of their baryons, what is the phase distribution, which will also depend on their accretion and feedback histories. And a related problem is the missing metals problem, which is often again confused with the galactic baryons. But finding a lot of baryons doesn't mean you have found all the metals, because we do not even understand the large-scale accretion process well. So finding a lot of baryons might just mean it is a lot of unprocessed metals that's just ionized by the metagalactic background. until we find the metals, it's very hard to say unambiguously that it was processed inside stars and came out of the ISM to the CGM and the IGM. So we have to find the galactic baryons and the metals together. And when the galactic feedback carries all these metals out from the ISM to the CGM, they naturally carry a lot of momentum and energy, and we do not really fully understand what happens to the energy. We often kind of hand-wavingly say everything turns into thermal energy at some point. But does it really happen? Where does it cool? Where does it recycle and come back? Does it even come back and contributes to the next generation of star formation? Some of these are very basic questions, but all of these are kind of unsolved. Now in the last 20 or 30 years, thanks to some great telescopes like Keck and HST, there have been a lot of observations in optical and UV. But in the hot CGM, which we can in principle observe in X-ray and millimeter, there have been barely any observations simply because these telescopes were not even designed to look for the CGM. So what I'm going to primarily show is how we can kind of push the abilities of existing telescopes to understand something and inform the simulations, and then how can we make more better informed decisions about the next generation of telescopes. So since I'm going to focus on the ionized CGM in millimeter, I'll just give a brief introduction of what SZ means in case you don't work on it. So the emission from the CMB is a nice black body spectrum shown here in the dashed curve. But as the CMB photons pass through any ionized intervening medium, it is inverse Compton squared, and the final distorted spectrum looks like this solid line. So if you plot the difference in the expected and the observed intensity as a function of frequency, you get this particular shape. And this integrated effect of distortion, which happens due to the thermal pressure of the free electrons, is called the thermal SZ effect, simply because it's thermal pressure. There are weaker SZ effects that we are not going to talk about, but this is the primary focus on our talk today. Traditionally, it has been used to observe galaxy clusters, simply because one, they are much larger in size, so you can resolve them well, even with a huge radio beam like 10 arc minute that was for Planck. And also because they have large thermal pressure, so naturally they have stronger SZ signal. But when it comes down to individual galaxies, one, they are smaller, so you cannot resolve them. We need at least some new generation telescopes like ACT and SPT, and also we have to stack upon a lot of galaxies to effectively reduce the statistical uncertainty and detect it. And when I say a lot of galaxies, it means at least roughly 500,000. Now the problem is, when you have an SZ map from CMB constructed through standard component separation, and you have a galaxy catalog, you can just blindly stack a lot of things and get something. But the interpretation of stacking can be extremely complicated unless your Y map is cleaned well and you have a very inhomogeneous galaxy sample. Suppose you have some galaxies that's cluster members and some are central galaxies, some are field galaxies, some of them are active, some are not. It's very hard to understand how a stack of 500,000 galaxies are going to behave like if it is very inhomogeneous. So we have focused on L-star galaxies in this particular stellar mass range and only focus on field galaxies just to avoid the intracluster medium, which has a significantly stronger SZ effect. And we also exclude any galaxy that could be individually identified as an active galaxy in terms of infrared color or the radio loudness. And also on the SZ side, one of the standard correction that is done is deep projection of cosmic infrared background that we of course do. But often we overlook the dust from our Milky Way, which is way more patchy than the relatively smoother cosmic infrared background. So we also make a cut based on the extinction in the high galactic extinction region. And we also remove all the galaxy clusters in the SZ map that are individually detected as SZ sources. One of the largest one is Virgo clusters, as you might have already guessed. And also we remove all the compact radio sources that are individually detected from the first catalog. So the problem with the compact radio sources are that we are already not stacking on the radio loud sources. So in terms of signal we are fine, but in the background region, if you have a lot of compact radio sources, they might bias your true halo or the background estimation, which in turn will affect your signal estimation. So just to test the effect of all of them, we have also stacked before and after all of these corrections. So all the red curves are the stacking results before corrections and all the blues are after corrections. Now even if you don't care about the details, you can visibly see that they all look different before and after corrections. So overall the average effect is that without these corrections, the final thermal pressure might look much flatter simply because your background might be underestimated and your normalization in the 1 kiloton can be overestimated. So the actual thermal pressure profile might look flatter. Now if the galactic feedback is strong, that might also give you a flatter thermal pressure profile. So there will be a degeneracy between the actual thermal pressure and residual effect of these artifacts. So you have to make sure these corrections are done before stacking. So we have now a clean Y map and a relatively homogeneous galaxy sample. So we stack in different mass bins. And this is qualitatively how the projected Compton Y profile looks like. We also make sure we stack up to a very large distance, up to 10 times the virial radius. So we have a signal-free region where we can fit the 2 halo term well enough. Also, just to clarify, 2 halo means all the other halos you are not stacking up on, but since they are around the galaxies in the 2D plane at any random redshift, they will also be stacked up on and will give an approximately constant emission here in the 1 kiloton region, and also will start falling as you are going off. So here, as you can see, we can fit the 2 kiloton pretty well here in the signal-free region, and only in the innermost region these black data points are above the background region. So we really needed at least a 1 arc-minute beam like ACT or SPT to resolve the 1 halo from the 2 kiloton. So this is just one mass bin. We repeat this for all the mass bins. We get the thermal energies and then plot as a function of halo mass. Now, if the CGM behaves exactly like massive groups or like clusters, we will expect the profile to either follow this blue dotted line or this gray dashed line. This is coming from existing literature based on either Planck or even ACT. And as you can see, the best fit, the red line, which is not obviously following any of the expectations. So this clearly tells you that the CGM is not behaving like a tinier version of clusters or groups. There might be many different interpretations, but before that, if you kind of squint, you might probably see that the shape is probably not just a power law. We fitted a power law simply because that's the standard. We try to see what is causing this apparent deviation from a power law. Now the green line is not a fit. I'm just drawing it to guide your eyes that there might be a different shape, and that might be because we have still an inhomogeneous sample, inhomogeneity within the galaxy sample. We have to split that up to figure out if two different populations are following two different YM relations and giving this apparent deviation from the power law. One of the simplest way to do this is just split based on quiescent and star-forming galaxies, as we expect the feedback histories to be different. But apparently 500,000 galaxies are not large enough to do that. So we now need a larger sample, which we have done now with WISE and DESI catalogs. So here we have 2.5 million galaxies. When we split, we have 0.7 million quiescent and 1.8 million star-forming galaxies. So more or less, the analysis remains the same, except that we are doing it for star-forming and quiescent galaxies separately. And now, as you can see, the thermal energy versus mass relation obviously looks very different for star-forming and quiescent galaxies. Now, one of the important thing here is that quiescent galaxies are just doing fine. They are still consistent with the self-similar relation down to a halo mass of 12.5. So, the relative strength of feedback and gravity doesn't really change with halo mass if we just focus on quiescent galaxies that are in the field and currently not active. So, depending on how you select your galaxies, you might get a very different interpretation of feedback. And star-forming galaxies are obviously deviating from the self-similarity, even visually you can see, and also you can see the numbers. So that means the effect of stellar feedback definitely has one real detectable effect, and it changes with mass. So one of the main takeaways here is that we cannot just focus on mass while looking at thermal energy versus mass relation. We also have to split galaxies based on their star-forming activities. Now lastly, how well are simulations doing? Short answer is not very well, which you can see, because the predictions from 3 different simulation shoots, Eagle, Simba and TNG, they are all significantly above our observations and also other observations based on Planck, ACT and SPT. For star-forming galaxies, it's really bad. The predictions from simulations are a factor of 40 higher, 40, not even 14. So we don't really know what is going on. That is such a huge difference that you cannot start to tweak small things and make things consistent. For quiescent galaxies, the difference is an order of magnitude, which is still bad, but not as bad as star-forming galaxies. Our guess is that since the simulations don't really treat the stellar feedback and AGN feedback physics differently, it's like the same physics and different parameters of opening angle and thermal energy input and time scales and all. That might be a problem since the the stellar feedback happens across the days, Canadian feedbacks are primarily in the nuclear region, and also the metallicity might have some effect, especially in the inner CGM. We guess that the way the feedback is treated in star-forming galaxies might be one of the reasons of this discrepancy. So having said that, I will leave you with the summary and take questions.
So Sanskriti, you consider the thermal SZ effect. There is another effect which is the kinetic SZ effect. Now, when the temperature is below, the virial temperature is below half a keV, the temperature in units of the electron mass is less than 10 to the minus 3. And 10 to the minus 3 is roughly the peculiar velocities of galaxies relative to the speed of light. Okay, so below half a keV, you expect actually the kinetic SZ effect to be dominant. And perhaps what you are detecting is no thermal, just kinetic. Have you looked into that?
But since we are just stacking on the galaxies, shouldn't the peculiar velocity will be averaged out and cancelled?
And not for for every galaxy there is some velocity field that it follows, right? So you would detect a net effect. Now, on average, of course, it would be either positive or negative, but then the question is, what is the coherence length of the velocity field? Yeah.
Yeah, I think usually for SZ, if we just stack upon the galaxies, the average peculiar velocity might significantly reduce the net case.
Well, it depends on the coherence length of velocity fields. And if you look at redshift surveys, the coherence length is hundreds of nanoparsecs. So it might be useful to look into that, because maybe you're just detecting the kinetic.
We haven't exactly thought about that because we thought the average effect might be kind of zeroed down, given that we have like 500,000 or even more.
And you can
galaxies.
distinguish kinetic from thermal by the spectrum, if you do it in multiple bands.
Yes, but we are starting from the SZ map, like the TSZ map. So those are constructed already by separating KSZ from TSZ. That's why we think it is unlikely that in the TSZ map there is some residual effect from the KSZ.
Thank you. Any questions, comments? Yes, Tony?
How much does your analysis depend upon having the 230 gigahertz data at the null of the SZ effect? I mean, suppose you had a lot more SC data, but it didn't have that frequency as a null in the effect.
Right. I think the CIB deprojection might be affected. Because when the SZ effect is getting down, the CIB has a relatively stronger effect compared to the CMB, if I remember the ratio of CIB to CMB. And that might overestimate. I mean, the CIB deprojection anyway is not a very good correction here. So without, I think, the 230 gigahertz where the TSZ is getting null, the CIB deprojection might be worse, if that makes sense.
Okay, if there are no more questions, let's thank our speakers.
We're going to stop doing 230 It's harder. It's a lot harder. People think it doesn't matter. I think it matters. Well, it's in pursuit of little R. Get little R without.
Okay. Hello, everyone. My name is Jiaxuan from Princeton University. Today I'm going to try to talk about two topics. They're all starting with dwarf, but one is dwarf galaxy, the other one is dwarf planet. They're both interesting. So let me talk about dwarf galaxy first. That's the far part. So like 3 decades ago, people came up with a problem called missing satellite problem. That means if you do an n-body simulation in your cold dark matter scenario, you find so many subhalos surrounded around the Milky Way like dark matter halo. Then if you think, okay, all the subhalos would host a satellite galaxy, then you will have 2,000, 3,000 satellite galaxies around the Milky Way. However, if you look at the sky, you count the number of Milky Way satellites, you only find 40 to 50 such galaxies. There's a big mismatch between the number of subhalos and number of satellites. But this problem was solved now because you can argue that not all subhalos can form galaxies. And that was the missing satellite problem before. Here I'm showing the current model prediction in the colored bands versus the number of satellites of Milky Way. This is cumulative. Now you can see the model and prediction looks pretty good. So one caveat about this is that we know Milky Way satellites very well because they're so nearby. We can go down to the mass function very deep. However, there is no systematic search for satellites around other mass galaxies. What do I mean by that? So if you look at the embedded simulation, the top row shows the embedded simulation of a Milky Way-like galaxy. You find subhalos around it. However, if you do the same simulation for an LMC, like Large Magellanic Cloud-like galaxy, this thing is 10 times less massive than the Milky Way. You still find subhalos around the halo. This means LMC-like galaxies should also have satellites. But what's the number of them? What's the probability of them? We don't know. Is there a missing satellite problem in this regime? We don't know. So let's do it. Before I show any observational results, let's look at the prediction. So here, the y-axis shows the number of satellites that you expect to have versus your host galaxy mass. Of course, as your host galaxy gets more massive, you will have more satellites. And our LMC is shown there to anchor the whole plot. The LMC has one satellite above a certain mass threshold is 10 to the 5.7. This is roughly the completeness limit once you go beyond 2-ish megaparsec. So LMC has only SMC, the Small Magellanic Cloud, as a satellite. So a poor guy only has one satellite. Then the question is, can we search more LMC-like systems and try to pop this plot with more data points? So let's do it. In my thesis, I started a survey called ELV's Dwarf Survey. It's kind of dwarf, a funny name. So the way of doing this is as follows. So we first find a dwarf galaxy host. Here I'm showing DDO 161, shown there. It's a beautiful edge-on-edge dwarf galaxy. Its mass is about 10 to the 8.3, similar to the Small Magellanic Cloud. It's at 6 megaparsec. So what we do is we take the image, we draw a circle, which is roughly the virial radius of the host galaxy. Then we search for fuzzy blobs within this virial radius. And we can find 1, this little thing, 2, 3, 4, something like this. So we repeat this process for a lot of host galaxies, and we get this. So the data points are the host galaxies we searched. The y-axis is still the number of satellites. And the theory prediction is shown in the background as orange. So you will see, OK, the observation isn't quite agreeing with the simulation, right? So if I would say this would be a too many satellite problem for the dwarf galaxy hosts. And why? I don't know. So for the system I shown before, the DDO 161, it has 4 satellites, which is 3 sigma beyond the theory prediction. So why it's so rich, I don't know. And another interesting thing about this plot is we see too many satellites problem at the left side. And in the middle, around LMC mass, you don't see many satellites over here. And why there's a dearth of satellites around LMC mass, we don't know. So of course, models could be wrong. Of course, dark matter might not be cold dark matter. But I think this is really exciting results, and there are a lot more to explore here. OK, so I'm going to quickly shift gear to dwarf planet. So this is a work led by Si-Hao Chen at the IAS. Briefly speaking, we were trying to find moving objects in the dark energy camera legacy survey, and we find these moving objects. It's shown here. The good thing about this is it's super bright. It's 22 magnitude, and it's moving slowly. What does that mean? That means it's far from you such that it's moving slowly, and it's bright means that the size of this thing could be large. So we went back to the data archive, tried to search for other detections. We find 20-year and 22 detections spanning 20 years. So we can fit the orbit really well. And the orbit looks like this. So it's a gigantic, a very elliptic orbit with a center axis of 800 AU, and the eccentricity is 0.95, very, very elongated. And that panel shows where it's located now with respect to Neptune and Pluto and Sun. So it's there. And if you calculate the size by assuming an albedo, you get 700 kilometers. This is roughly the regime where you would call it a dwarf planet. So if you compare the size of this with other known dwarf planets, you will get a third largest dwarf planet for this guy. So really cool. Then this is itself cool, but is there anything better than just finding a dwarf planet? So we think yes. If you talk about trans-Neptunian objects, meaning that the objects beyond Neptune's orbit, there's an interesting thing is the Planet 9 hypothesis. So people have been thinking about there might be a ninth planet beyond Neptune. And the evidence for that is if you plot all the trans-Neptunian objects' orbits on this plot, you will see their orbits are kind of clustered along a specific direction. The explanation for this is that there might be a massive planet called Planet X, which will kick out all other orbits, only keeping these things, because the orbit of Planet X has a specific direction. That's the evidence for Planet 9. Then the question is, how does our new trans-Neptunian object add to this scenario? We plot the orbit. It's completely outside of the clustering. The left-hand side shows the orbit. The right-hand side shows the longitude of perihelion, which is similar to the left-hand side. Our object is here. The clustering is here. So it's completely outside of the clustering. So maybe this argues against the existence of Planet 9. We did more simulation. So in this figure, we showed the evolution of this TNO with and without Planet 9 existence. The blue curve there shows the scenario when there's no Planet 9. This TNO can be there doing OK for 1 gigayear. But once you put in a Planet 9, it will be kicked out within 0.2 gigayear. So the fact that we observe this guy now probably means that Planet 9 isn't there, or the parameter that we take for Planet 9 in this simulation was wrong. So I'm going to stop here and take questions.
Thank you. Two brief questions. One, with respect to the satellites of dwarfs. Obviously, if there are also satellites of a bigger halo,
right,
there would be a tidal loss of so the number of satellites. Okay, after that I'll ask a second.
Yeah. So the beautiful thing about our survey is that we only select isolated dwarf galaxies. They're not part of the bigger halo.
Okay.
So we know the satellites are the dwarf satellites, not the satellite from a bigger halo.
No, but also you lose satellites from the small halo as a result of the tidal.
That's true. That's taking into account in the model.
When you count, you need to take the tidal radius into account, that you're missing some that were outside the tidal.
So in both simulation and our observation, we all take everything within the virial radius. We do not go beyond the virial radius for both searching and comparing with the simulation. So
yes, but I'm talking about the tidal radius. The tidal radius is smaller than the virial radius. So around your dwarf galaxy, there is a tidal radius because it sits in a bigger halo.
Right.
So that tidal radius means that everything outside of it was lost. So you need to correct for that. That's what.
But that shouldn't change the number of satellites.
It would, because you lose all the satellites outside the tidal radius. There is a tidal force that separates them from the host. You see. So you're losing everything outside the tidal radius. So you have less satellites around your host than originally. But it's something to consider. It could be very important for the LMC, for example,
But then it's even more confusing that you have an overabundance
Yeah.
of small masses.
Yeah.
Exactly.
Yeah.
Like,
Yeah.
it essentially is.
But one has to correct that.
Yeah.
Yeah, exactly.
Yeah.
And about your dwarf planet, very briefly, how was it formed in this orbit? It must have been perturbed by planets or what?
Yeah, so we run some simulation. I think this thing might be from the outer Oort cloud, got scattered in.
Oh, in.
Yeah. But that's one scenario, and yeah, we don't quite know how it was formed.
But in the outer Oort cloud, the chance of an encounter is extremely small because
Yes,
it's dilute.
yes.
Maybe a passing star or something?
Yes, maybe.
Please.
About the dwarf galaxies, have you obtained spectroscopic confirmation for all your satellites?
Yes, so the way we measure the distances is through something called surface brightness fluctuation,
Yeah,
which is independent from the spectroscopic observations. We have some velocities for some of them, but not all.
Because SBF won't work for star forming dwarfs. If they're
They-
and they're okay.
Yes, they kind of work if you carefully mask out the star forming region. We did a lot of tests for this, but yeah, I agree. For like getting more velocities would definitely help.
Please.
So how accurate should I expect the masses of these dwarfs, stellar masses of these dwarfs?
Fantastic question. That's a big uncertainty. So I think the error bar is 0.3 DAX-ish. Yeah, 0.3 DAX is my. So for this DDO 161, if you shift by 0.3 DAX to the right, it's still an outlier, I think.
Very interesting. Keep making discoveries in many other frontiers.
Thank you.
Thank you.
Can there be someone to help with this?
Do you have an HDMI cable? Do you have an HDMI plug?
If we hadn't kicked Pluto out of the list of planets, the planet 6 would be planet 10 instead of
Yeah, I think it's missing. But closely to planet X, X is 10. Okay, there's another one. We're absolutely it's
Oh, there we go. Okay. Yeah.
All right. Yeah. So I think we have had quite a few very good, observational talks, and so, finally it's time for the theorist to say something with very few plots, and so now we are with that, today I will be talking about Planck star remnants. This is a new dark matter, proposal that me and Professor Loeb put out, I think, in June this year. So what are Planck star remnants, and why should we care about them? So one thing which has been of interest to not only astrophysics but also quantum gravitational theories is the black hole information paradox. And what happens when you have a black hole, and what happens really when you think about like gravitational collapse. So when you talk about Oppenheimer-Snyder-Dunt model, right? How do you make like a quantum gravitational analog of that, and like could you attempt to regularize the central singularity of a black hole using quantum gravitational effects? So that is something which Carlo Rovelli and Francesca Vidotto worked out in 2013, and they found out something known as Planck star remnants. So they found out that if you consider effects from loop quantum gravity, then it could be a possibility that during the stage of gravitational collapse, while reaching at the scale of a Planck size, there would be some quantum gravitational repulsion, and that repulsion will actually not allow the matter field to completely collapse into a singularity. And so instead of like a Schwarzschild black hole, you would be left with like a very small object which would have a size on the scale of the Planck scale, and they called it Planck star remnants. They actually worked out its stability as well, and it's quite a stable object considering loop quantum gravitational effects. And its mass would be that of the Planck mass. And so the question that we asked was, could these objects act as dark matter candidates? And that is actually pretty well motivated, as I will just discuss why. So as I shared with you, the collapse will halt at the Planck scale, and the interesting part is this would be something which will interact completely gravitationally. So you would not have these objects interacting very strongly with normal baryonic matter, and so they would almost be like pressureless dark matter. And at the same time, they would be very hard to detect using our conventional medium. And they would also be non-radiating, because causally what happens is, for the external observers, you cannot distinguish a Planck star from a very, very tiny black hole as well. And so causally, if you would try to differentiate like a Planck star remnant from like a primordial black hole, that's very hard as well. And so what we wanted to do was, we wanted to consider like a interior metric and an exterior metric. So you have like an interior matter field, and that is collapsing. So you have like a spherically symmetric collapse going inside, and then you consider that there are some particular loop quantum gravitational effects on the inside, and then you try to match the interior and the exterior metrics at some particular junction using the Israel junction conditions, and now if indeed such relics can be used to describe cold dark matter, the required relic number density would be this much. And this is really consistent with the usual estimates that we would like with cold dark matter, because the number is something which is not too high, like this is not like unrealistically high, and at the same time these objects could satisfy the properties of simple, stable, compact like gravitational objects, which we would like to associate with our usual dark matter candidates. And what did we do in the paper? So in our first paper, we considered like an LQG corrected modified homogeneous interior, and we matched that to a Schwarzschild exterior. So basically what we wanted to understand was, if for an exterior observer, like would the observer causally see any difference from a usual Schwarzschild space-time, and we applied the junction conditions. And now, if loop quantum cosmology also has a very interesting feature, that it allows for a bouncing model. And we observed, of course, this is not for a cosmology, but we observed that a bounce can also happen in this case for the interior metric, because we are considering loop quantum effects on the inside. And so the central singularity is actually prevented, and this leaves like a finite density core, which is exactly what we would like in the case of a Planck star remnant. And as the collapse stops at the Planck scale, the remnants have the mass of the Planck scale as well. And so these are the essential identifications of these objects, and we we wanted to understand whether like such a process occurs, and if that does, could we observationally ever detect such objects, and if we want to actually detect such objects, what kind of early universe processes would be needed for that as well. And so, here I have, like I only have like 2 plots. I mean, you guys had like some wonderful plots in your papers, but like I only have just 2 plots, right? So this is my first plot, and here we have, basically compared like the mass scale of the like other well-known dark matter candidates like WIMPs, neutrinos, axions, and PBHs, and you would see that that PSR, the abbreviation that we gave for Planck star remnants, lies in a very intermediate window. So it's not like your usual particulate dark matter candidates, and it's not as high as primordial black holes as well. So it lies in a very intermediate window as compared to its other counterparts for dark matter. And now the natural question is, what early universe mechanism can generate such objects? So initially, we wanted to see whether if we have Gaussian statistics for perturbations in the early universe, would that be enough? And so, initially we did the same thing as people have been doing for primordial black holes, and we wanted to test out what would be the appropriate amount of like enhancement of the amplitude of the power spectrum in the early universe for achieving such candidates, and that was pretty high, right? And that would like only be consistent with a very strong stochastic like gravitational wave background. And for people who are like very much infatuated with inflationary theory, these kinds of enhancements can only be done in quite exotic scenarios like ultra slow roll models, or like certain classes of constant roll models and stuff like that. And so you cannot actually get this with slow roll inflation, and that is something which has been true for primordial black hole production as well. And then we wanted to, of course, we have, some of the, great people from LIGO over here. And so we are very happy to say that LIGO has ruled out, Gaussian production for PSR. And in fact, instead of Gaussian, actually, something which can work out is non-Gaussian statistics in the early universe. So if we find out that perturbations in the early universe instead have like tremendously or like significantly non-Gaussian features, then it can result in collapse, which could lead to primordial like primordial black holes, but also it can actually be sufficient for PSR to create enough amount of dark matter to account for its current estimates that we see today. And so the final conclusion would definitely be that PSR is viable if it is seated by non-Gaussian primordial fluctuations, or if you want to word it another way, non-Gaussian primordial fluctuations are the best way to create Planck star remnants in order for that to explain dark matter. And with that, basically what we wanted to understand was, could, instead of simple stuff like WIMPs, axions, or primordial black holes, could we actually have a dark matter candidate which is completely motivated by quantum gravitational considerations? Like the counterpart of Planck stars in string theory is foosbals. Somebody can possibly think about foosball dark matter or things like that, although foosballs are used for something completely different. But yes, what we wanted to find out was, could we have completely quantum gravitationally motivated dark matter? And the answer for that is yes, but we would need some very specific scenarios for that to be true. And yeah, with that, I would like to thank you guys for your attention, and yep.
Just a comment. Such a Planck relic would be 10⁻⁵ grams, like the mass of a dust particle. how many of these, if that's the dark matter, how many of these black holes are passing through our body during our lifespan? I mean, that is, we keep thinking about black holes, but if the dark matter is black holes of this mass, they keep passing through our body all the time.
Yeah. And in fact, like there was a paper earlier this year by Robert Scherer where he like discussed this stuff exactly. If like very small primordial black holes could be permeating our body, of course, it could have very significant tidal effects, but like if the effects were like very strong, I don't think any of us would be alive talking about this stuff right now. So hopefully they are not.
These are negligible gravitational effects. They cannot do anything other than gravity.
Right.
Please.
Just one question really, and I might be naive. One of the tests we do for dark matter candidates, we see how at least our sun would be affected if these candidates were to be placed in the sun. So assuming this is just gravitationally interacting with matter, it should then change the nuclear reactions and should change the luminosity of the sun ever so slightly. There's a pretty good hold on these numbers. So I'm just wondering, is that something you've thought about? Like how much of the dark matter, let's say, would exist in the sun, given that it is, an object bound by gravity? And does that affect the,
Yeah, that's a really good. Yeah, that's a really great direction to like think about. Actually, we have mostly thought about constraints which we can get from like early universe data or stuff from LIGO till now. But yes, I'm not really sure how. We would have to like derive like a particular framework for this. But like, I definitely think that could be something interesting to do, and not only for like Planck star elements. I think that could be something interesting to do for like primordial black holes in general. That could be good, yeah.
Okay, we have time for one more question, and then we have to take a photograph. So, please.
Hi, thank you for the talk. I'm just curious, would these stellar remnants have non-zero spin? Because would that prevent you from flashing the Schwarzschild at the exterior?
Yes, that's a really good question. And so, that would tie back exactly to, loop quantum gravity. And so, like the initial papers, which like Rovelli and Vidotto made on Planck star elements, they considered like a Schwarzschild spacetime. So we really, I don't think people have considered, like spinning Planck stars till now. That could be something very interesting. And I think in general there are like good reasons actually to like not think of like spinning primordial black holes as like dark matter candidates. I don't remember the reasons right now, but there are some. And so I'm not sure if like spinning Planck stars would do us any better, but like in terms of like a purely theoretical idea, I think it can be something very interesting to like possibly work out if you can have like spinning Planck stars. Yeah, that could be something interesting.
Okay, let's thank all our speakers.